other works on archive. Yes, it's being recorded. I got it. No problem.
Sorry.
Let me just. That's okay. So I'm part of some collaborations, the JPAS and its ancillary surveys, J+ and S+. So JPAS is a photometric survey with 54 narrowband filters that is soon to be deployed. We have now the mini JPAS that is like a survey made with a Pathfinder camera. So very soon JPAS itself will be providing us with data. And J+ and S+ are twin telescopes, one here in Spain, together with the JPAS telescope. And S+ is in the Southern Hemisphere in Chile. And they all have, if I'm not wrong, 14 passband filters, narrowband and SDSS-like filters. That's a great question. I think, I'm not sure, but I would say by the end of this year, I think it's going to, I think has started to observe a few things, but to provide data, maybe internally by the end of this year. So, but I'm not going to promise anything. I don't speak for the entire collaboration. And I'm also part of the Cosmos Statistics Initiative, which is the coin that you can see here. So we try to solve a few problems in astronomy using statistics and computational techniques. I'm going to go over through here. So in my future, well, this is my past. My future maybe in CENTRA. I have applied to a position as investigadora. So who knows? Have to wait for the results. Oh, it doesn't want to go. Okay, so I'm going to briefly talk about Gaia-ESO survey. That's the survey that I joined when I went to Poland, and the data that I've been using. So the Gaia-ESO survey is a spectroscopic survey that has observed about 115,000 stars in the Milky Way, and these are the general characteristics of the Gaia-ESO survey. So has had 340 observing nights between 2011 and 2018. The instruments used are the ESO Very Large Telescope, Flames instrument, and Giraffe and UV spectrographs with these respective resolutions, and also uses Gaia astrometry. Has provided high quality atmospheric parameters, chemical abundances, and radial velocities for these stars. Up to 31 abundances derived with UVs. And it has observed stars from all the Milky Way components, thick disk, thin disk, halo, and bulge. And also stars in all of evolutionary phases. And 71 open clusters and 15 globular clusters. And I refer to you these two papers if you want to know more about the Gaia-ESO survey, Gilmore and collaborators 2012, and for the UVIS instrumentation spectral analysis, Smiljanik and collaborators 2014. The data, the final data release has been just made public. So this is the ESO website. So if you go there, you can get the data and do your own science with it right now. And this is one of the papers, the final papers that has been accepted for publication now in June 6th. So it's very new. So I marked it there. There will be an accompanying paper by Gilmore and collaborators that's still in review. So if you want to see all the results from Gaia-ESO in detail. So now I'm going to enter the real topic of this presentation, which is about the supermetal rich stars. But before that, I'm going to talk a little bit about radial migration, because this is the core of what I'm going to talk about that. So first of all, what is radial migration, right? So let's all agree here and see what it is. So it's the change of stellar orbits, that means guiding radius, in relation to their birthplace position due to gravitational interactions, and especially with non-axisymmetric structures, such as bars, arms, disks of spiral galaxies. So stars that are in spiral galaxies, they have their orbits, that are influenced and change due to these gravitational interactions. And I must remind you that the Milky Way is a barred spiral galaxy. So it is expected, radial migration is something that is expected to be seen. So there are basically two types of radial migration. So one is blurring. So it's this epicyclic movement of stars in eccentric orbits from their birth radii with no change in angular momentum. So you have this epicyclical movement, and it's very eccentric. And basically, this is how the star migrates to other radii. And you also have churning, which is the change in angular momentum. So the churning is when you really have this interaction with the bar that makes a star change in angular momentum and reach other radii. And at the end, I mean, they also reach smaller eccentricities. So before I'm going to talk about the work itself, I'm going to give you a preview on other works. So this is a work by Khorpeskov and collaborators, 2020. They made a few simulations, and they explore exactly the effects of low eccentricity in meteor-rich stars at the solar vicinity. And here you see some of the results of their simulation. So these colors, it's basically the change in age of the star. So a star that is very young is in blue. So as it starts to move around the galaxy, it's independently of their original eccentricity. So you see some of them are very eccentric. Maybe I can point it to you. Some of the originally may be very eccentric. And then as it moves around and it gets older, it gets a near circular orbit throughout the galaxy. The same happens with stars with low eccentricity in the beginning. As they move around, they tend to have a more circular orbit. So the eccentricities they tend to get smaller. And then you can see also how the stars they move, you know, to different distances from the center. I put a few parameters here for the Milky Way so we have an idea of what's going on. So this is already a spoiler from the paper. We put this as a reference. So you have the thickness that you would expect from the thin disk of the Milky Way. So the stars that have these features, they're expected to be in the thin disk. Those that have these features are expected to be in the thick disk. And if you want to see some references where they mention these features, please, these are the references. So you can see that, well, the thickness is basically the most important thing for thin disk and thick disk, right? So you have that the thin disk should be more or less between 0.3 kiloparsecs in thickness. The same thing, 0.9, it's the thickness expected for the thick disk. So I will display this sometimes here so you can see how these stars behave of our sample. I'm going to talk about that in a while. And it's very interesting to have in mind that radial migration can cause the thickening of the disk. So it means that these stars can reach higher distances here, higher than the thick disk, if you will. So just have this in mind because we're going to come back to that pretty soon. Another interesting paper is this one by Kordopatis and collaborators 2015, where they use observational data from the RAVE survey. And well, there's a lot of information here, but eccentricity plays a very important role. So I will call your attention for those in higher metallicity. So here is the metallicity in terms of iron over age. So these are the most metal-rich stars in their sample and in different radii around the Milky Way. So this is basically the solar vicinity. So you can see that the distribution of eccentricities here peaks around 0.15, and it's usually lower than 0.2. So these are, you know, metal-rich stars that have low eccentricities, which kind of reminds you the simulations that I just showed to you. And their ages for these very metal-rich stars can be also pretty high here, even around 18 years of age. There's also these results from the Lemmost survey. They also test radial migration, and they find two sample of stars. All of them are super metal rich, but one is very young and the other is very old. And this very young is usually associated with the thin disk, right? And they also explore some of their features. So this is the age determinations. These are the old subsample. This is the young subsample. And I'm mentioning these papers right now before I mention my own, so you can have these things in mind. And I particularly find this paper very interesting because it has some very similar results as ours, although they used an entirely different survey for that. Here, there are many different parameters that they find that indicate radial migration from the stars. Oh, sorry. The first one here, I'm going to talk about the Z max. So it's that thickening I told you about. So if you remember, stars that would be in heights above 0.9 kiloparsecs should have probably have suffered some sort of radial migration. So you can see here that there is a considerable amount of stars. So this red group here is the old supermetal rich. It's the one that we're most interested. So you can see that there is indeed some stars here. This is the guiding radius. So the guiding radius is a concept of basically, it's a radius that the star would have if the orbit was 100% circular. So we know it's not. We know there is some eccentricities. We know it should be an ellipse. But if we kind of modify that to know what to expect, that would be the radius if the orbit was 100% circular.
Excuse me, what is the axis? Horizontal or vertical?
The x-axis?
Yes.
Here?
Yes.
Here is the G is guiding radius. So RG means guiding radius.
And on the vertical?
It's just numerical. This is a histogram. So it's the amount of stars that have this. This is the distribution. I'm sorry, I failed to describe this a little better. Yes, you're right. So these are histograms. So the amount of stars that we have, the distribution of these stars given these parameters. So as I said, this is the guiding radius. This is the pericentric radius. So you can see that this is like the closest the star gets to the center of the Milky Way in their orbits. So you can see that for these old supermetal rich stars, they're mostly concentrated here in 9 kiloparsecs. So they have migrated quite a lot because the solar vicinity is around 6 to 7 kiloparsecs, more or less.
Sorry, and what is the difference from plot to plot?
It's basically the blues are the young stars. Yes, this is what I'm trying to show you. So this is the guiding radius, this is the pericentric radius, this is the eccentricity that I've been talking about.
So it's 3 different things.
3 different things, yeah. So I'm sorry, this is from their paper, so I don't have control of the size of how they write it, their axis, but yes, so this is eccentricity. This is the maximum height, so it's Z max, the one I told you about the thickness, the apocentric distance, and this is the binding energy. But what really matters for us is basically these 3 and Z max. But I'm gonna go back to this when I show you our results. So using Gaia-ESO, we're looking at these stars in the solar vicinity, these old super-metal-rich stars. And briefly, I just would like to say this is a work that has been done in 1.5 years at the time that I've been in the Nicolaus Copernicus. And this is a paper that is in review right now. So this is the one I'd like to talk to you about mostly today. And what questions do you expect to answer? So yes, let's just go back here and look at the title. So old super-metal-rich visitors from the inner galaxy. Okay, so we're looking at stars that are currently in the solar vicinity, and they display these features of super-metallicity and old age. Okay, so what do you want to do with these stars? What do you expect? We would like to analyze, and what do we expect to answer? So if we have a sample of stars independently of their metallicity, can we identify a chemical enrichment flow? So this is something I'd like to stop a little and explain to you what is a chemical enrichment flow. So if you have a group of stars, they are formed, they evolve, they produce chemical elements, and they inject this material to the interstellar medium, which will form new stars and so on. So this next generation will have a different metallicity than the previous one. So you would expect that to have steps of metallicity with steps of age in stellar groups. So you have different groups of stars that would display this kind of feature. So when we're looking at that, so we wanted to identify, can we see some sort of chemical enrichment flow in the sample? So what are the general characteristics of the sample? I already gave you a few, like super-metallicity, old age, but kinematically, what are their features? And where did they come from? Thin disk, thick disk, bulge, inner galaxy. And do our results agree with the literature?
So let me summarize. So we want to understand super rich stars that are here around us that come from somewhere.
Yes, because their metallicity is not
Not the same.
in agreement with what one would expect in the solar vicinity.
Okay.
So this is a sort of mystery in the sense that we would like to know why they're here. I mean, I already gave several spoilers here about radial migration, so we're gonna get to that. So about our sample quickly, we used only stars that were detected with UVIS because the resolution's better, the chemical abundances are better, and our total sample is 1,827 stars. But for this analysis in particular, we're using 147 stars for the MMR sample. What is MMR? Most metal rich. Okay, so MMR is most metal rich. If you see it here, this is what it means. And we're also using parallaxes from Gaia, isochrone heating using Unidom, it's code, orbits calculating using Delphi. And these are the abundances we use, okay, to verify this chemical enrichment flow and everything that I will explain just now. And I put a little note here, notes that we're not using lithium. I'm gonna go back to the lithium at the end of the presentation. So just be aware that we're not using lithium here right now, although we have it measured. So all these stars are in the solar vicinity, as I said, all around 2 kiloparsecs from the sun. So this is the X and Y heliocentric coordinates and X and Z heliocentric coordinates, so you can have an idea of where they are. And we got those, okay, so all those 1,827 stars, I'm sorry. And we used hierarchical clustering to cluster them together by abundance, by chemical abundance, using those 21 abundances I mentioned. So what it does is basically it puts together groups of stars that have similar abundance in all those chemical elements that you've seen. And this is a very strange plot that you're seeing. It's called Dendrogram. So basically, while it groups, it connects these different groups of stars as in the shape of a sort of a tree. So you can, this is just a zoom, okay? This bottom part is a zoom. There's a zoomed in part of this larger part here. You can see that we can basically cut wherever we want, and we can create different groups. So for example, if I have a cut around here, I can separate all those stars in 1, 2, 3, 4, 5, and 6 groups. And as I go down this tree, I can separate in smaller groups if I want. So I can have a big group, and then inside I can have a smaller groups, for example, of stars. And they should have some sort of similarity. I know this is kind of maybe a little strange, but well, hierarchical clustering is just basically a very simple kind of machine learning that does that. So you can use any parameters you want. It will cluster together the ones that have similar features. So I'm just showing you these 3 cuts we made because for this analysis, we use this big cut here of 5 or 6 groups, and this smaller one here to cut the big group into smaller groups. I'm gonna get to that. So why did we use this? Well, first of all, it's non-parametric, so it assumes nothing from the stars. I don't have to give it any parameters, just the ones I wanted to cluster. I don't have to make it dependent on anything. It groups objects in terms of similarity, and you can use these, in my case, 21 dimensions at once, but you can use 100 dimensions if you want, if you have it. So you can do it however you want. Can use 2, can use 3, can use 100. You probably use more computational power, but it will do the job. And the large groups, as I told you, you can then separate these groups in terms of their chemical abundances. So these are the 21 chemical abundances I told you about. And these are the groups that come from that. So this is basically 1 sigma of confidence interval. Here you can see for all the groups. And you can see that we have these very metal-rich stars here. You can see this. This is the abundance. It's X is each of these elements. Okay, so in this case we have carbon over age. So these are the abundances for carbon over age, sodium over age, and so on and so forth. So you can see that it goes from very metal-rich to very metal-poor, and we're going to focus on this group here. And by the way, we're going to use just as benchmark this group that we call a solar group, because this group that has metallicities around 0 are the ones that are closest to the metallicities of the sun. So the sun is the benchmark around 0. So we use this group just as a comparison for a few things.
So what does it mean?
It doesn't mean anything. It just means that it has less, anything very important, just it's less metallic than the sun. Negative means that. So it's more metal poor in relation to the sun. If it's over that, it's more metal rich than the sun.
It's a logarithmic relation.
Yes. Okay, so again, this is another version of that plot, but focusing on the super metal rich stars. And you see these colorful groups are the subgroups that I told you that we cut lower. So we can actually get this very, very metal rich group and then separate it in other subgroups. So we separated here in 5 subgroups of richness. Then you can see, for example, this purple one is very, very metal rich in relation. It's usually even above the 1 sigma bootstrap we did here. And you have the other groups here, the light green, dark green, pink and yellow, and orange, sorry. And then we compare it to the solar group in general. This is just the same plot basically, but using the distributions. These are ladder value plots, which is a more general version of the box plot. So you can really see how the stars in each group show their distribution. You can see these are the medians here, these little straight markers, and then you can see, how they change. I'm not going to go in detail here because it's a lot of information here, but just for you to have an idea of what is going on here. So you can see, for example, this purple group has this distribution usually very much higher than the others, which is what we saw previously as well. This is just a table that I put with the median metallicity using iron over age, the dispersion, maximum values, minimum values, and also magnesium over iron. And just for you to see a little bit how it changes. So yeah, the purple one is the most metal rich, and how it goes from purple to dark green, how it changes, but we don't have to focus on the numbers, just focus on the plots. So this is also a plot of magnesium over iron. So just a little comment, this variation of magnesium over iron and other elements, for example, carbon, they give us a hint of where this, what was the environment that produced these stars. So it was probably in a region that there was a lot of contribution of supernovae type 1, A, 2, and AGB stars. But this is not the focus here. But this is important information. So this is just a little bit about the age determination isochrones that we used. These are the median metallicities for each of the subgroups. All the colors here are kept the same, so you can follow whatever happens throughout this analysis. And the median age here is around 11 gigayears. So they are very, very old, which is this is very near 11, I think. Yeah, this too. This is, I think, over 11 gigayears. So the medians are very, very high. And then you can also see how more or less the solar group is distributed here. So it pushes to younger ages. So you can see that usually our groups are much older than the solar, for example. And so here start to look at the kinematic features that I presented to you with the other papers. So you can see that these stars, they reach heights that are much higher than the 0.9 kiloparsecs that I told you about. So you can see that a lot of them could be, classified as thick disk, but much more than that, they go higher in this range. So it happens to all of these stars. And then you can see their current guiding radius. So this is the radius they are currently, so all near the solar vicinity. So here around 6 to 8, more or less. And that's the distance from this galactic center, okay? This is a very similar plot to that one, but we changed the x-axis for the eccentricities. So you can see that they usually have these very low eccentricities, just like the simulations we saw, that these stars would have low eccentricities, and that their migration would be probably due to churning. If you remember, right in the beginning, I was telling you about blurring and churning. These are the two kinds of radial migration I was telling you about. So yes, the low eccentricities, they are connected more to churning than to blurring. So, and I will convince you with their distributions, okay? So distributions near this range 1.5, they're very near circular orbits. And you have just one that is just a little above 0.2, but it is still very, very low, which doesn't change anything. It's still very low. And now I'm going to convince you once and for all that these stars have migrated. Now it's like we have maximum heights, we have eccentricities, and now we have also a lack of metallicity gradient. What is a metallicity gradient? Okay, so it is expected in our galaxy, not just our galaxy, but this is something that is done in other galaxies as well, is to analyze how the metallicity changes from the middle of the galaxy throughout its radius. So these are models for 11 and 8 gigayears for our galaxy that would predict the formation of these stars at different radii. So stars with, say, metallicity, when I say metallicity here, I'm roughly saying iron over hydrogen compared to the sun. So if we have something around 0.2, well, it would have been formed at 6 kiloparsecs from the galactic center. That's what is expected. And so on and so forth. And you can see that in all our groups, these stars are much, far away from these models than one would expect. Somebody could say, well, but this, the solar group, this thing in gray here, this group in gray here, is also kind of, shifting around. There are two things I'll tell you about this. Well, first of all, this is the kernel density, so I'm not showing exactly the stars, but how they distribute in this area. And the kernels are concentrated within the models. So it means that the values are concentrated near to the models. So what you would expect is more or less being, respected there. And it has a broader distribution when you compare to these supermatter rich stars that have this flat pizza shape distribution. So you can really see they're kind of, following a flat trend throughout different radii. So for example, I really like this purple group because it's so extreme that you can really see everything very, very obviously with it. So you can see that not even the density touches the model. So the dots themselves that are the stars, they're very far away from the models. And one would expect that they were formed in the very near regions of the galaxy, you say 2 to 4 kiloparsecs, for instance, but they're so far away. I mean, they're here around 6, around 10. They're nearly at 10 kiloparsecs, so they have really migrated a lot. So this is the guiding radius, and I did the same thing here, showing you for the pericentric radius. So you could say, well, if they are moving around the galaxy when they're the closest to the galactic center, where do they go? So you can see that, well, some of them reach the models, it's true. So we believe that these stars that get closer to the models, they have probably migrated due to blurring, that epicyclic movement I told you about. So with no change in angular momentum, so there's an effect of blurring in the stars. But those that still are disconnected, are very far away from the model, we think that they have migrated due to churning, that other kind of radial migration that happens with the interaction with the bars or the disks of the Milky Way.
So with the years, they will be disconnected from us.
I think they will start to reach the outer regions of the Milky Way. I believe that, but I don't think they will, they won't fade away to nowhere.
Further away.
Yes, that's what this predicts. Yeah, this is what is expected in a few gig a year. These models, by the way, are from Magrini and collaborators, 2009. So if you're interested in these kinds of things, I refer you to this paper. Please check it out. So yes, so a lack of metallicity gradient proves, it's like a very strong evidence that these stars have migrated. So overall, this is a take-home message from the sample. So when you look at all supermetal-rich stars, you have to check out all these parameters and see if they fit the thin disk, thick disk, or something else. In our case, they didn't fit anything. Some of their parameters could be attributed to thin disk stars, others to thick disk stars. But when you combine these characteristics, the high ages, the supermetallicity, the low eccentricities, the maximum heights they achieve in the Milky Way, and the lack of metallicity gradient, these are evidences that these stars have migrated radially. This is why they don't fit the general metallicity of the solar neighborhood. Okay, so I'm gonna quickly talk about a little bit about lithium. Remember that I told you in the beginning, please pay attention that lithium is not used to cluster these stars. We don't use it here, but keep it in mind that I'm gonna go back to that. So yes, so one of the questions that arose from this study is, can radial migration help explain lithium depletion? Okay, so there's also another question that you could ask is, can the lithium in the atmospheres of dark stars serve as a proxy for the lithium in the interstellar medium? So I'm going to briefly talk about lithium. Lithium is a very unique element because when you look at these chemical enrichment flow that I told you about, well, it should maybe increase, it is expected it to increase with when you create new elements or creating more, you're increasing the abundances of elements, you should increase lithium as well. But lithium is very delicate and it's more likely to be destroyed in the atmospheres of stars, the interiors of stars, than being created. So what we see, I took this from Guillaume and collaborators, 2019. Models predict exactly what I'm telling you, so that the lithium should, given the overall metallicity of these stars, the lithium abundance should increase with increasing metallicity. Okay, this is what the models predict. But observations show that for stars with metallicity above solar metallicity, so remember that 0 is the solar benchmark, so the sun is here. So metallicity is above the solar metallicity, we should see an increase. But in fact, what we're seeing is that lithium is being destroyed. Okay, so the abundances, they fall. And this is due to this phenomena. So in this paper, they explored the effects of radial migration. So for some reason, which I don't know either, what's causing it, but for some reason, radial migration is playing a role in the depletion of lithium, okay? They have studied that these stars have migrated from the inner galaxy to our neighborhood, solar neighborhood. And now we're working on this ladder. It's nearly done to be submitted in the next few weeks. So we're probing the lithium abundances in these stars. And what we're seeing is the same thing. So here is for that second level of clustering that I told you. I showed you a large one, a middle one, and a small one. So here we have 11 groups. This is the entire sample, not just the super metal rich. You can see that there's a trend, an increasing trend until metallicity, solar metallicity, and then there is this infall trend. So why do I have like two trends, one above the other? So these stars here on the top, lithium is, as I said, is a complicated element. So in these stars, we have actual detected lithium. Okay, so we have measured lithium here, and we have detected its abundance. And this lower level here that you can see, there's a gap, is the upper limit expectation. So we don't know exactly what are the abundances of these stars, but this is the maximum that should have. So this is an upper limit estimate, okay? And then you can see here some age effects that we're exploring right now. So there's even an age gap between detected ones to the upper limit. So since the upper limit is usually lower, you can see they're usually older stars as well, at least for those with above solar metallicity. So we can see that with age, these stars, they tend to deplete more lithium. The older they are, the less they have. And here, this is basically the same plot. I'm just adding the data from Guillaume and collaborators 2019 that I showed you in the other plot. So you can see that the trend is quite similar until solar metallicity, and this infall trend is seen in both data. And here I'm showing you specifically, so I'm gonna go back to a second. This is the most matter-rich group. So it's the most matter-rich in both cuts, the higher cut and the middle cuts. And you have those other groups that I told you, the green one, light green one, dark green, purple, yellow, orange, and pink. So we're actually now the next plot, we're going to just look at these stars. And this is what we see. Oh, sorry. This is what we see. So we have the different distributions, of these the lithium abundances, giving the iron over hydrogen features. So remember, the purple one was the most metal rich, so it's over here. So you can see that it has very little lithium when you look in comparison with the others. So it's the most metal rich, but it's also the one with less lithium in it. And these two, you see these two distributions, the colored one and the gray one, in this case, has nothing to do with the solar values. It's just that the ones that have the same densities, colors of the plots, of the dots, sorry, are referred to the detected lithium abundance. And not in the others, the gray ones are the upper limit. So you can see that, for example, here, the most metal rich, I mean, it doesn't even have detected lithium. It's always upper limit, the upper estimation of what it could have. And it's also the oldest together with this pink one. And the pink one also has just 2 detected lithium. The rest is all upper limit. And when you start to decrease in age, you start to see a little bit of the detected lithium, a little bit more than just the upper limit. But basically, when you look at these very old groups, you can see that they have very, very little lithium. So conclusions. Well, as I said, I asked in the beginning of this last part, the lithium part. So actually, just a second. For the most metal-rich group, the oldest are also the most depleted in lithium and are the ones that migrated from the innermost regions of the Milky Way. So if you remember, this one, the purple one, also migrated from the innermost regions, was very disconnected from the models. Also the most, the one most depleted in lithium. And the question I'd asked, well, since our data doesn't fit what you would predict from the models, well, the lithium cannot be used as a proxy for the interstellar medium, the lithium in these stars. So this is something that has been done for quite a lot, to use these stars as values for the interstellar medium. But we're seeing now that this cannot be done because of this depletion. Muito obrigada. Thank you very much.
Questions?
We have to throw out the
Throw out? I hope not.
let's say that we-
I don't think we have to throw out anything. I just think that this is how science is. We think something is one thing, and then we investigate
that I
further.
know, of course.
Yeah.
But since the papers are wrong, I have to throw out. We don't need to be political.
I'm not. I'm not.
So the papers are wrong. They make conclusions which are certainly wrong as far as you were saying. So, you know, you have to start now working in another direction, I think.
Yes. First of all, I'm not the first person that said that. It was Guillaume. Okay. So I'm gonna put the blame on him, but he's together with us in this paper too. So it's my fault too. Okay. Yes, I would say that now we have to think very carefully when we use lithium for any kind of analysis, because of this delicate nature of lithium, because it can be easily destroyed. This also happens, if I'm not wrong, with beryllium a little bit, but this is very, very strong with lithium. So it's just a matter of really being careful with what you're doing and not make assumptions like that. Like it could be a proxy for ISM, for example. It could be a proxy for other things. Say it could be, let's say it could be in the future, if we find out that it's really like this, that it could be a proxy for radial migration, for example. Something to think about.
What I'm trying to say is that, are they wrong 10%? Are they wrong 100%?
That's a great question. I don't know.
But we can take something from those papers that said that.
Sure. Yes.
Can you suggest some physical explanation, connection between level of metallicity and special characteristics?
What kinds of special characteristics?
Why the movement of stars from the soul?
The movement of, okay. Can you ask that again? Let me think about it. If I can connect the abundance.
Something that I can make some connection. Let me try. So you produce those stars that have, let's say, the center that have some eccentricity.
Yes.
Then they start to rotate.
Yes.
But they are already old stars, right? Because they are metal rich.
Well, in the beginning, no, they are rotating. They're rotating, and they get older. As they are rotating, they get older. And at some point, they reach the solar neighborhood, and they are already old at this point.
But they are already metal rich.
They were, yes.
They are old in that sense. Created.
Yes, they have been created.
They
have been created in a region that was very rich in metals when they were created. So this is what it means. But they are old, and so what means that it means that it's even at that time when they were formed, there was already a very metal rich region where they were formed. Basically, this is what you can gather. But yes, I understand your point, because you would expect a metal-rich population of stars to be young, to be part of this new generation that has been chemically enriched, as I said, in the chemical enrichment flow, which, by the way, we don't see here because we have basically old stars, not different ages of stars. So they have been formed in the inner galaxy, and also in different radii within the inner galaxy, because you can see by this lack of metallicity gradient, that it would be compatible with different radii here because of the iron metallicities. So it would be in the inner galaxy, but even in the inner galaxy, it would be in different radii. Each of these groups, each of these stars.
You already mentioned this, but I was wondering, like, if you have any hint of what makes lithium so special, like any density, but now as compared to other elements, like something like that.
Well, okay. First of all, disclaimer: it's not my specialty, so I don't know lithium very deeply. What I know is that it can be very easily destroyed. It's easier to destroy lithium than to create it. It can only be created in very specific situations. So, for example, you can see that there is a phenomenon called the Lithium Dip. So if you look at stars, I'm gonna go back here. Oh, sorry, I think I passed it. In different stages of stellar evolution, you will see that the lithium will increase, but then at some point, if I'm not wrong, within the giants or something, it will decrease. So there's something going on inside the star, some sort of maybe convection, some sort of mixing inside that is getting this lithium and destroying it. And then for some reason, when the star continues to evolve, the lithium goes up again. So it's a mystery that a lot of people are trying to understand, but it's a big problem. Is this more or less what you? Yeah. Okay.
So when you mentioned lithium is missing in the 21 elements, there was one more element missing, oxygen.
There's several elements missing.
No, but it's a very important most of one. So is there any specific reason you found that in the past?
Yeah, I mean, it's a technical reason. We had more abundances, as I told you. UVIS has up to 30-something, 31 abundances it has provided. So we used 21. So what we wanted is to maximize the sample. So to maximize the sample, we wanted to get those elements that would have been detected for sure in the maximum amount of stars. So oxygen didn't make the cut. I'm sorry. So for most of the stars, probably oxygen wasn't measured. And so we didn't use it to cluster. But for those that, I mean, if you're interested in oxygen for some reason, come talk to me. We can see the ones we have oxygen measured, and then we can do something with it if you have any ideas.
More questions? I think we have time for this question, so
Thank you very much.
thank you again.
If you enjoyed the video, like and subscribe.